Hello, I am Ravi Pandurangan, a senior faculty for IITJ Physics, training students for IITJ entrance examinations in Andhra Pradesh, India. This is the continuation of my physics classes. Okay. So I want to continue the demonstration class which I was taking up earlier, sir. So previously I was taking a disk on which a force F acting on it. It was given by the interactor with me on that day. And to find out the force required so that there is accelerated pure loading, and we assume that the frictional forces forward in any direction we can assume from the force equation. If it comes negative, then the arrow mark should be changed, that's all. So we can write the linear equation. The linear equation is F plus F equal to ma, that's first equation. The force in the forward direction F plus F equal to ma, and the torque acting upon the center of mass is F minus F into R, that is clockwise and anti-clockwise torque resultant. Torque equal to I alpha, we know. We are taking the torque about this, therefore the moment of inertia should be taken about center of mass only. Therefore mr square by 2 into alpha is A by R. So R gets cancelled here. F minus F equal to ma by 2. This is equation 2. Now from this we can just simply add 1 and 2 and get 2F equal to 3 by 2 ma, or F equal to 3 by 4 ma. So this is the minimum force required for pure accelerated loading. So we have used the principles here: force equation, linear equation, and rotational equation we have written. That's torque equal to I alpha. About which point we are taking the torque, about the same point moment of inertia has to be taken. That's very important. The other way to do is only one equation we can take directly. Suppose the frictional force is here and the force tangential is here. I want to take torque about the point encircled here. If that is the case, the frictional force does not provide any torque. There is only one torque, that is F into 2R. Torque is I alpha. I is about which point we are finding the torque, about the same point I should be taking. So parallax here we can use mr square by 2 plus mr square. 3 by 2 mr square alpha. Alpha is A by R. One R gets cancelled and here R gets cancelled. Therefore F is 3 by 4. So in one step we get the same answer, the force required. So instead of taking up center of mass, two equations. The other way is, that day we were discussing taking the energy equation. How can we use energy principle to calculate? It is a laborious process, but let us see how we can use the energy principle. So here we take again the same disk and friction force F, and here the force applied is F. It's accelerated pure loading. Now we have to find, let us say it has gone to a distance S at some instant of time after time t. So work done by all the forces, by all forces equal to delta KE, change in kind kinetic. Work done by all the forces equal to delta KE. Now let us see what is the work done. Linear, you have force here F and linear displacement S. So Fs, and again frictional force is F in same direction. So Fs small f into S. Of course Fs cos theta, theta is 0 in the same direction. Next, one important point, there is rotational work done also which has to be considered, very important. frictional force tries to reduce the angular velocity. This applied force tries to increase the angular velocity. The force which tries to increase the angular velocity, positive work done, tau theta. Just like how we have F is cos theta, here tau theta into cos theta. If it is in the same direction, to increase the angular velocity, then we take positive quantity. If a force is trying to decrease the angular velocity, we take it as a negative work done, rotational work done. So that has to be considered when we take the total energy into consideration. Therefore, let us see what is the work done by friction. The body tries to accelerate, having an angular velocity in this direction, omega increases, but this friction force tries to reduce it. Therefore, minus F R, that is torque, tau theta, that is the work done, rotational work done by friction. And similarly, F, about this point I have taken, that is plus, because it tries to increase the angular velocity. So F R, that is torque into theta again, equal to half mv square plus half I is mr square by 2 v square by r square. Because we have to consider the total energy. Change in kinetic energy is due to the work done by all forces and work done by torque also, which has to be considered. Therefore, you have here very important equation here. When it has gone by S, suppose you traveled S, that means the point of contact has moved on the ground. The point of contact has moved on the ground. That is theta equal to arc by radius. Because the point of contact is moving on the ground. Whatever distance it has moved, theta can be calculated from that. Theta is arc by radius. So S can written as theta r. Therefore, so S is theta r plus S is again theta r. Or simply I can leave this as Fs to simplify it more easier way, minus Fr, theta is S by r, so that I can cancel r, that's equal to plus Fr theta equal to 3 by 4 mv square, because half mv square of 10 3 by 4 mv square. Now what we have concluded here is work done by friction, rotational, and work done by friction, translational, they cancel out. Therefore, net work done by friction is 0. In other words, there is no rubbing at the point of contact. When there is no rubbing, no heat is generated. No heat is generated means no work is done. That's why the terms got cancelled. Now we can use F. Now theta we have written as F theta r, can written as F theta r plus F theta r. So we can write as 2F theta r equal to 3 by 4 mv square. Now we can write omega square minus omega naught square equal to 2 alpha theta. There is an angular acceleration. Assuming that F is greater, angular velocity is increasing. Omega naught is 0 starting from rest. So I can write theta as omega square by 2 alpha. But omega square is v square by r square 2 alpha. Because v by r is omega. Therefore I can write 2Fr theta is nothing but v square by 2r square alpha equal to 3 by 4. 2Fr into 3 by 4 and v square. Therefore here we get r gets cancelled here. So v square gets cancelled here. So we have omega square v square by r square to 2 alpha. Alpha is nothing but a by r I can write. Therefore a by r. Now I can cancel r square. I can cancel 2. I can cancel v square. Therefore F equal to 3 by 4 ma. cross multiply it. So we get the same here. Even though it is laborious, it is required to know the concept. In certain areas, we can use work for energy conservation. In certain areas, force equations are very easier. In certain areas, torque equations are very easier. So we found in three ways: taking about the point of contact, taking about the center of mass, using energy conservation. Okay, and whenever there is a pure rolling, work done by friction is zero. I want to represent some more techniques which can solve it in a very easier way. Some problems are there. It's a familiar problem. Let's see where we have a pulley, a 1 kg body suspended here, and here we have a 2 kg body. Here you have a 3 kg body. I think you are familiar with this. Now they asked you what is the acceleration of this, after how much time it will hit the pulley. Here one technique is, I will take a point on the string here and I will just hold it, cut it and hold it. So how much tension you feel, that much mass is connected directly there, removing the whole quantity. So that I want to check. So I will take like this, I will hold it here. This is 2, this is 3. Tension is the internal force on the system, whereas the same tension is external force on one body. If you consider one body, it is external force. If you consider system, it is internal force. Therefore, on the system, the external forces are 3G and 2G down. This tries to pull down, this tries to pull down. Net force by sigma m is the acceleration of system. System means 2 kg moves up with certain acceleration, 3 kg moves down with certain acceleration. That is how much? 3g minus 2g, that is g, by sigma m is 5. Directly we get the acceleration of 2 kg and 3 kg. In other words, 2 kg is moving up with g by 5, this is coming down with g by 5. Holding it in your hand at rest. Now I will take one of the body. This is coming down, 3g minus t equal to ma is g by 5. So t is 3g minus 3g by 5. That is 15 minus 3, 12g by 5. Now I got the tension here, T, and here also T. The wonderful point here, when you are holding, the tension here should be 2T. That 2T is nothing but 24G by 5. In other words, I am removing this whole thing, 1 kg, and placing here 24G by 5 means the equivalent mass is 24 by 5. So 24 by 5 is here. Now we will get the acceleration of this body. Acceleration of this and acceleration of this are same. Therefore, net force by mass again. Net force is 24 by 5g minus 1g by total mass 24 by 5 plus 1 equal to acceleration. Therefore, you get how much? 19g by 19g by 5 by 29 by 5. That's equal to 19 by 29g. So that's the technique we use. Instead of using with respect to pulley and all that, we just cut this and hold it. How much is the tension you experience? 24g by 5. Remove the g, connect it here, you get the mass and you get the acceleration. Once you get the acceleration, remaining things are very easy. After how much time this will hit? Half it is clear. So this is one of the beautiful technique you can adopt. I would like to represent some more techniques which are very useful for examination point of view, because time is also very important. Not only the logical, not only the procedures, time is also very important. Now, if I take a rod connected by a string like this, rod weight or mass is 4 kg and this is 2 meters in length. Now the question will be asked is suppose a little surface ball is a fixed point. Now usually the question asked is tension is how much and force given by hinge is equal to dash. What are the force given by the hinge and what is the tension? Here very important point is tension acts on the rod. What are the forces? Hinge is down, tension is upward. Wall will give a force parallelly or upward or downward. That we have to decide. We cannot say wall gives only a force towards right. How to decide? We have 4 kg down, tension is in this direction. Definitely this will be a component theta here. This component I have taken the angle, I think I have taken 60 degrees you can take for example. Okay, 60 you can take. Theta at 60. Okay. Now if you take 60, definitely the component t cos theta, this is t sin theta. T sin theta is less than mg definitely. When the whole body is suspended vertically, t will be mg. How can the component be equal to mg? There is no possibility. That means there should be some other force upward. That means hinge gives Fy upward, Fx forward. That's the logic here. Otherwise, triangle will not be completed in equilibrium. All the forces when you put in a triangle, the vector sum should become 0. That is why we have applied this concept. Now, talk about this point. Force into perpendicular distance. I will drop perpendicular here. That gives you anti-clockwise torque. This force into perpendicular distance gives you clockwise torque. Fx and Fy does not provide any torque. Therefore, mg force into perpendicular distance is 1 equal to t into perpendicular distance is x. That is how much? Sin 60 is x by that is 2. 2 into root 3 by 2 is x, that is root 3. So t into x is root 3. That is 40 by root 3 is the tension. Tension cannot be equal to the weight. How the logic is, weight is downward, tension is at this angle. When it is the component, definitely the component cannot balance it. There should be something else upward. That means the hinge should give a force upward also, apart from forward direction force. How do you know forward direction is there? T cos theta is there. Something should be there in the forward direction. Therefore, that's the way we can find. And once you get T, the very simple upward forces equal to downward forces. Fy plus T cos theta is here. T sin theta. So Fy plus T sin theta equal to mg, that is 40. T sin theta, sin 60. Therefore, and again Fx equal to T cos theta, that is T by 2. Therefore, you have Fx as T by 2, 20 by root 3. We got Fx. Now to get Fy, Fy is 40 minus T root 3 by 2. That is T is nothing but 40 by, I can take yes, 40 by root 3. Therefore, you have 40 minus 20 there, 20. Now, Fx square plus Fy square under root gives the net force given by the hinge. Therefore, you have 400 plus 400 by 3 under root. 1600 means 40 by root 3. That means it happens to be the same answer. The tension in the string is 40 by root 3. The force given by the hinge is also 40 by root 3. But it is an inclined at an angle theta, where tan theta equal to Fy by Fx. It's a very important concept. Now some more problems of the same type I would like to discuss. Sometimes we will be given a wedge of mass capital. All are frictionless contacts, and you have a rod resting on it, and we have wall here such that the rod is constrained to move in this direction only. Now we want to know the relation between A rod versus A wedge. We want a relation. Once we get the relation, we can use conservation of energy and calculate the velocities. Okay. Now what we shall do is, we will take a point of contact on the wedge and immediate point of contact on the rod. On the rod and on the wedge is 2 points which are in contact. As the rod moves down, the point on the wedge moves away like this. As the rod moves down, the point of the wedge moves away like this. So the diagram will be like this. Here the rod is moving down and the wedge moves away like this as the rod comes down. This point on the wedge moves because the point on the wedge cannot, an atom on the wedge an atom on the wedge that has to move horizontally, it cannot come down, atom cannot be displaced away. And the point on the rod should come in its own direction like this. A point on the rod moves in this direction. Let us call it as AY or Y we call it. This is X, this is theta, this is theta, this is theta. Sin theta is Y by X. What is the beautiful point here is, take the point on the rod, take the point on the wedge which are in contact. That point on the wedge you observe where it is going at a particular instant, and point on the rod where it is going. Draw the diagram. Now you get a relation. Now x sin theta equal to y. If you differentiate once, you get Vx sin theta equal to Vy. Differentiate again with respect to time. Ax sin theta equal to Ay. That is the relation. Ay is nothing but rod acceleration. So acceleration of the rod equal to Ax is nothing but wedge acceleration. Acceleration of the wedge into sin theta. So it's a wonderful point here. Once you know that. Once we know this, the energy equation can be written very easily. That is, as it moves this side, the velocity we can find, and total normal reaction acting. We should not check the weight. Whenever one body is resting on the other, the important point is normal reaction. So normal reaction, let us check. Mg of the rod is vertically down. This is 90 minus theta, this is 90 minus theta, this is theta. This side we have mg cos theta in this direction. From the wedge we have normal reaction. That is, on the rod mg cos theta is this side. This side we have normal reaction. But the rod is moving down with some acceleration. Therefore, acceleration of the rod is net force by mass. That is mg cos theta minus n by mass of the rod. We got one equation for acceleration of the rod. Net force on the rod divided by mass. When I say net force, the force in the direction of motion only. Other force is not required because the rod is constrained to move along the wall. Now what is the force acting on the wedge? The force acting on the wedge is only normal reaction. Of course, from the ground we have another normal reaction which is of no use for the movement of the wedge. So you should not take weight of the rod is moving. We should say normal reaction making the wedge to move, normal reaction acting on the rod. We should not call it as our weight. We should call it as normal reaction. If we are standing on a still floor, it is equal to the weight. If the floor is moving down with acceleration or moving up with acceleration, normal reaction will change. So the better word is not using weight, normal reaction, contact force. So So this is here theta, and the normal reaction in this direction. This will be theta. This will be 90 minus theta. Normal reaction on the wedge is opposite in this direction. On the rod, up. Which body we are considering, on that body the forces should be written. Therefore, one more you have n cos 90 minus theta, n sin theta. N cos theta will become, of course, this forces of no use because that does not move the wedge. Therefore, wedge moves by n sin theta. Acceleration of the wedge is n sin theta by its own mass. Force acting on the wedge in the x direction divided by mass gives you acceleration of the wedge in the x direction only, because wedge cannot move under the ground or up. So once we get these two, we can substitute the value of n in this equation and solve using that equation. AR and AW absolute values also can be known. Is it clear point? Now two more problems I want to tell you in this regard. A wedge is on the floor. A sphere is here on the it is in contact with the wall and the wedge. All the contacts are frictionless. The solid sphere is constrained to move downward. It has an acceleration downward only. It falls down, but AS is not equal to G, because there are some forces contact whose N is there, component of N is upward. Therefore, you cannot say it is a freely falling body. This moves with A down wedge. I want a relation. This is some theta. Again, we go to the point of contact. This point on the sphere and this point on the wedge are in contact. After some time, how the diagram happens? The wedge moves away. The point of contact definitely should go horizontally. It cannot move downward. And this point should move down, because this point comes down in contact with here. This point on the wedge moves forward. This is theta, and this will be theta. So once again, let us see. The point on the sphere comes vertically down. Again, it should be in contact with the wedge. It cannot be in the air. But that point A is in contact with the wedge of different point. The same point is in contact with the wedge now with a different point on the wedge. The point on the wedge which was in contact with the sphere moves away horizontally. This point is no longer in contact with that sphere. That's the point. So theta, sin theta is y by, we will take tan theta. Tan theta is y by x. Tan theta is y by x. So y is x tan theta. Differentiate once, dy equal to vx tan theta. Ay equal to ax tan theta. That is ay, acceleration of the sphere, equal to acceleration of the wedge, because wedge is going in the x direction, into tan theta. So in this way we get the relation. Again, by contact forces we can get the velocities, or we can get the acceleration, individual accelerations at a particular time. So once again, the point of contact on the wedge moves horizontally. The point A moves vertically down. Again, that point A should be on the wedge, because the diagram will be like this now. The point A will be on the wedge. Therefore, we can use the tan theta term there and get the relation. So, in this kind of problems, the main point is we have to check the point of contact. That becomes very easy. So one more problem I would like to present. We have a system of pulleys sometimes given like this. Let us check this. Once you know this, the remaining you can easily delete. And this is in contact to the top. Here we have B block, here C, here A. A is having a velocity at a particular instant 1 meter per second. C is having a velocity 0.5 meter per second. I want velocity of B at that instant. So let us check how to do this problem. System of pulleys we have, and 3 blocks are attached. Irrespective of their mass, we need not worry about the mass. We can get the relation between their velocities and accelerations. Now this is moving up with 0.5 at a particular instant. This is having 1 meter per second at that particular instant. At that instant, what is the velocity of it? Now let us, one constraint equation we can write here. Length of the string cannot change. So this plus this plus this plus this plus this remains a constant. So I can write A, B, C, D, E. So A plus B plus C plus D plus E is a constant. That is length of the string. Let us say this has come down by x because he has already given downward direction. So let us assume the proper direction x. And let us say this has gone up by y. We don't know. Let us say y. This already it is given in the question going up. So let us say this point has gone up by z. Very simple technique. This is coming down already given. Let us say at one particular instant it came down by x. At that instant it went up by y. If this pulley goes up by y, this has gone up by y only. Definitely. Because center of the pulley connected to the block. And here this has gone up by z because arrow mark already given upward. Now let us connect a relation. New string length. In other words, we have taken a photograph at one particular instant. Again as they were moving, again another photograph you are taking. The system appears like this. So you have A plus x. A plus x is the new length. Now B minus 0.5. It has gone up plus C minus 0.5. It has gone up. This is fixed, no doubt. It cannot move. Therefore, B minus y, C minus y. This has come down. So this has gone up. So D minus Z, and this is how much? Plus E minus Z equal to L again. Once again. A plus x. Next, this has gone up. So B minus y. This cannot move. C minus y. This has gone up. So D minus Z. And this length has decreased. E minus Z. L is nothing but A plus B plus C plus D. So L will get cancelled with A plus B plus C plus D. Therefore, we have x minus y minus 2y minus 2z equal to this E also get cancelled. A plus B plus C plus D plus E gets cancelled. So x minus 2y minus 2z equal to 0. We got an equation. Fundamental point is take a photograph. What are the lengths? Take another photograph at another instant. What are the lengths? The length cannot change. Therefore, velocity dx minus 2vy minus 2vz will be equal to 0. Now vx is how much? 1 meter per second given. Minus 2 vy we don't know. Minus 2 vz is. We should not put a minus sign here because downward we assume x also assumed downward. Here we assumed it moving upward in the direction of motion. So we should not put minus 0.5 here because already we assumed upward. Plus z only we assumed. So you should be very careful. If you had put z downward, then you should. Therefore, what we write 0 point because that is the most important point. otherwise the whole answer goes wrong. Now these two get cancelled. Vy is 0. In other words, at that instant, the block is at instantaneous rest. Very important point. So here in this problem, what we come to know is the constraint equation. The string length cannot change at any moment.